Good afternoon, everybody. We'll continue from this previous lecture to discuss magnetic circuit and how to solve magnetic circuit. I will just refresh your memory. Previously, we found that we can use equivalent magnetic circuit to solve for flux density, current, anything that's unknown. And simply we said we are going to represent the magnetic circuit as a reluctance, which is equivalent to resistance, and magnetomotive force, call it F, sometimes we call it MMF, and it's equal to N times I, because the current is responsible for building the magnetic field, and it increased by the number of turns, so you multiply N times I, which is equivalent to voltage, and the reluctance as resistance, and we said it's equal to the length of the path where the flux flow divided by mu, permeability of the material, mu, and the cross-section area of the core. And the flux will be flowing in the magnetic circuit like current in electric circuit. So simply you can say that F, which is the voltage, equal the current, flux time the reluctance with the resistance. So that's simply what we get. And we're going to deal with, from this concept, it's really easy to solve magnetic circuit if we do that analogy. And we did simple circuit before, simple magnetic circuit like a core shaped like a rectangular, and one time like a toroid, with air gap, without air gap, and we did that. So today we're going to have an extra example, so we can have strong understanding for how solving the magnetic circuit. In this circuit, we have, or this magnetic circuit or magnetic system, you have a core made from ferromagnetic material, and the dimensions are given here. So you can figure out the length of the flux path in each limb. The relative permeability of the core material is equal to 1200. And we know that to find the permeability of any material, you got to multiply mu naught, which is the permeability of the free space, times the relative permeability to get the whole mu. So mu C means permeability of the core is equal to mu naught times mu I. And mu naught, it's should be known, it's 4 pi times 10 to the power of -7. That's mu naught times mu R, it is given always in the table or in the problems, that's equal 1200. When you multiply both, then you can get 1.508 times 10 power 3. And always when you multiply this quantity, and you'll find in your calculator, find 0.000, no, just multiply it by 10 power 3 or power 4, so you can get like 4 digits. You don't simplify. So that's the mu R. That's the first thing you can get the permeability of the core. But we want to know what the problem about. This core has air gap 0.5 centimeter, and it's assumed that magnetic leakage and fringing are neglected. What's flux leakage? Flux leakage, if you have core like that, just I'm sketching one part, and you have the coil like that, and you have the current, so the magnetic, if you continue, the magnetic flux going everywhere, so part passes through the core, and there are parts they do not go through the whole core, they go in the air like these 2 rings here. There are many, not I just show it in simple way, there are many rings, but they are small. So here the assumption they are going to be neglected. Why you are saying so? Because if you do not neglect it, so the flux phi that we assume here, it's missing part. It's not exactly the same. For example, if the total flux is, let's say 100, there will be flux leakage 2. So what's left 98, but we'll assume here the all 100 going through the core. That's the meaning of the assumption. Assumption 2, because it's very important to understand what does it mean each one. So that's the leakage, neglect, because it's a very small portion. It will not affect our calculation. The second thing, neglecting fringing. What is that fringing? It happens only when you have air gap. And let me show you what look like fringing. If you have core like that, and there's air gap in the middle, as you see, we assume that the flux will go through the air gap in the same way in straight lines as we assume in the path of the flux. But that's not true. Practically speaking, that you will find that like that. There will be bending on the side because there is a gap, so it's not going straight, just to be like making fringing, around. We are going to neglect that because it's a small portion, like 2%. So is everything in straight line to make our analysis simple. So that's, the assumption that we are assuming in this problem. It's not okay. Okay. The magnetic material has a square cross-section area. So if it has cross-section area and you look at the width of the core, it's 2 centimeters. So it means going depth 2 centimeters. So you can say that the cross-section area, if you make any cut here in this, you will see it look like a square 2 by 2 centimeters. So the cross-section area where the flux going perpendicular to cross-section area is equal to 2 times 2 centimeters square. So it will be 4 centimeters square. And remember, always we got to convert it to meters square. So we can say that the area of the core is equal 4 centimeters square, 2 by 2. Let me make it clear so in your view that it's 2 centimeters by 2 centimeters, because it looks like a square like that. So it will be equal 4 centimeters square, and that's 4 times 10 minus 4 meters square. So that's the first thing. All right. So, and then the dimension, you're going to use the dimension to calculate the length of the flux path through the core. You got 2 coils here, and the source obviously here, 10 amp, it will go through the N1, which is 500, and then it go in this direction, the last turn, then it go like that. And then in the end, will go out 10 amp. So obviously, you got on both sides 10 amp in both turns, and each are 500. So we got like 2 sources of magnetic field. The magnetomotive force of each is equal 10 amp times 500, which is 5,000 and ampere turns. So you can say now we have the source here and there. All right. So you can do that. You got 2 sources. We call this F1, and you have the other source, F2. F1 is equal N1, I1. We have 500 turns, and we have 10. That's 5,000. And ampere turn, you can write like that. And the magnetomotive force, second one, is equal to into I2, but I1 and I2, they are equal because I just proved it the same circuit. So you have 500 times 10, which is equal to 5,000 ampere turn. Let's now go back here. When you look for the flux flowing in this core, you can say that if you have the turns on the side, so the flux will be flowing here. Part will go there, and then part will go on the other limb. And actually, you can say that you have one here, and you have one in this path, and you can assume even that it's in this direction. So you have like phi1 in this direction, and you have phi2 in this direction, and then in the middle will be like phi1 plus phi2, right? Like current, exactly. Phi1 and phi2, and added phi1 and phi2. Okay, so you got two of those. And now, since we know that we have phi1 and phi2, and both they will be in the middle, let's now look for the length of the path. For the first one, to calculate the reluctance, you need L and mu and A. So you can say that we have like 4 reluctance. The first one, the first path, it's if you look at this these letters B, so follow me, B, A, F, E. That's the first one. Rectangular, but missing one in the middle, right? So that's the first one you are going to calculate. This is reluctance. So you got to calculate this length. So what's this length? From point B to A, when you look at it, it's 50, right? Or less, no less, because I mean we see 50 coming from here. So the 2 centimeter in the middle. So you divide it to 1 centimeter from the right, 1 centimeter from the left. Means that's this part is 1 centimeter. That's 1 centimeter. So you got to add to the 51 and 1, that's 2, right? So you got 52. So BA is 52 centimeter. Agree? All right. And the same thing, EF, the same, 52. So you got 52 on the top, 52 on the bottom. So what's left? AF. AF, it's 50, the same thing, it's 50. And you got 1 centimeter on the top, 1 centimeter on the bottom. I'm talking to this 1 centimeter. So we got another 52. So you got 52 on the top, 52 on the bottom, 52 on the left. So you got like 3 times 52. So that's the length of the path of phi1 in this side. All right. BA. So let me just write it down. So to organize your solution, you'll say, okay, that's the reluctance. Make a table like that. And then not to forget, you write the path. So the first one, I'm going to call it R1. And we said from A, B, A, F, E. And we found out that the length in this case is in centimeter. It's equal to 52 times 3. That's the first one. That would be considered like our L1, corresponding to R1. All right. Now I'll go back to the same diagram and look for the second one. R2, it's B, C, D, E on the right-hand side. It's the same, symmetric. It's easy problem. So it will be the same 52 times 3, right? So we'll go and say R2, and I will write it's from B to C, D, E. It's the same one, 52 times 3. That's L2. All right. Now let's go back and end on in the middle. End on in the middle, the length is equal to from point B to point E. It's going to be the same, 52, right? But you observe that there is air gap in the middle. So you got to subtract 0.5 centimeter from this length. So you'll say that the core, I'm talking about the core only, the core length in the middle limb is equal to 52 minus 0.5. So let's just go ahead and do that. And we'll call it R3. And this is the middle limb called BE, and just you write core, because there are two things, core and air gap. I'm talking about the core. So it's equal to 52 minus half, which is equal to 51.5 centimeter. All right, that's call it L3, because I'm calling it R3. So everything is done except only the air gap. The air gap, we always call it RG, air gap, and the length is equal to 0.5 centimeter. That's your LG. That's a very important step, and that's why I put it in table. Very important to find the length. That's the one that you just have to be careful, and you see, I mean, in the middle, the length of each straight line, and you add it. Once you did that, everything is solved, because they are doing that to calculate the reluctance, which is analogy to the resistance of the circuit. So what you're going to do? Well, we know that the formula, the reluctance is equal L divided by mu A. You got A and you got mu, we just calculate it. That's the, I think, previous page. Yes, that's mu C for the core, 1.508, 10, 3. So just to put it there, mu C is equal to 1.508 times 10 R3. And we know mu naught, when we deal with the air gap, we use only mu naught, which is equal 4 pi times 10 power negative 7. All right. So what's next? You just go ahead, and the circuit here you do it. You say you got resistance to the right, or reluctance R1, and the one on the right hand side, that's R2. And in the middle, you got two, one for the core and one for the air gap. That's R3, and this one RG. So that's your circuit. R1, R2, R3, RG. And now I want to find the values of each reluctance. It's easy, because I have the table, I have L, I have AC, I have the area, cross-section area, I have mu, so just substitution. Let me write the equation for you. So the first one, R1, will be equal L1 over mu C AC. And then I'm not going to waste the time for putting the values, because you have L1 in the table, just put, oh, but you got to do it in I have to do at least one to make sure that you can convert. You convert it to meters. So it's 53 times 3 centimeter, and then you multiply it by 10 minus 2 to make it meter. And mu C, we have mu C, just to put the mu C in this one, will be 1.508 times 10 power 3, that's mu. And AC, that's in the top here, it's 4 times 10 negative 4 meters squared to the convert. And then you calculate the reluctance one. The same thing, reluctance 2 will be the same. They have the same length, and they have, so I'll say that the reluctance 2 is equal to reluctance 1. Reluctance 1 was calculated, I mean, so you can check if you like to solve this when you go home. 2.58 times 10 to the power of 6, and the unit ampere turn per Weber. R2 with the same value, they are equal.
Excuse me.
Yes.
I hate to stop you in the middle of a play. If you were at 53 times 3 up top, there's not 52 times 3.
You're talking about 53 times 3 here?
You had the very top, the L1, would it be 52 times 3 instead of 53 times 3?
Oh, yeah. I wrote it here wrong. It's 52. That's right. Yeah, you're right. I copied it the wrong way, yes. It's 52 times 3, yes. You're right. And reluctance 2 is equal to reluctance 1, because the same dimension. So I just write the same answer here, ampere turn per Weber. All right. And R3 is different, it has different length. So I'll write R3 is equal, and the length of R3 is equal to 51.5 times 10 negative 2 over the same thing, square 0.8 times 10 power 3 times 4, 10 negative 4, and I get R3. I did the calculation, and it's equal to 0.82 times 10 power 6 ampere turn per Weber. What's left? The air gap. But just I want you to remember the values here. It's all 10 bar 6. And the one to the right of the left, like 2.5 something. And the one in the middle, 0.82. And now we're going for RG. The air gap, it's LG is equal 0.5 centimeters times 10 minus 2 meter. And I'm going only to use mu naught. 4 pi times 10 power negative 7. And the area not change, it's the same dimension. So it will be like 4 times 10 negative 4. And when we calculate the value for air gap reluctance, it's equal 9.9. 10 to the power 6 ampere turn per Weber. If you remember that we did in previous lecture, we always find that the reluctance of the air gap is the biggest value, right? It's the most effective value, is the air gap. Yeah. All right. So what next? Remember in this one, the first thing that you need to calculate air gap flux. Air gap flux means phi G. Phi G, the flux in the air gap is the one in the middle, which is equal phi 1 plus phi 2. So actually, I need to solve this magnetic circuit to find fluxes, flux phi 1, flux phi 2, and then I add it. So I got to think about how can I find flux? I just solved the circuit. The magnetic circuit I need. That's the magnetic circuit. You have here phi 1. And you have here phi 2. And then in the middle will be phi 1 plus phi 2 in the middle branch. Look at it as current. So you just solve the circuit. I will sketch here back again. That's R1, R2, and in the middle, that's R3 plus RG. And you got here F2, which is equal 5,000. And you got F1, which is equal 5,000. And I have the value for all reluctance. So here's phi 1, and here's phi 2, and here phi 1 plus phi 2. You can use many techniques to solve the circuit. Let me just get the simplest one. You will say that F1, the voltage is a voltage, is equal phi 1 times R1 plus the voltage across R3 and RG, which is equal phi 1 plus phi 2. That's the current in the resistance R3 plus RG. So I'll say, and phi 1 plus phi 2 times the resistance R3 plus RG. If you just simplify, you look for phi 1, you found out that phi 1 is multiplied by the total resistance in loop 1. If you call this loop 1 and you call loop 2, so it will be R1 plus R3 plus RG, all multiplied by phi 1. And the one in the middle, the common one, will be R3 plus RG multiplied by phi 2. So that will be the equation for F1. For F2 will be the same thing. You'll find that in loop 2, you multiply phi 2 by the total resistance in loop 2, which is R2 plus R3 plus RG. So you have R2 plus R3 plus RG, all multiplied by phi 2. And in the middle will be the common or the mutual reluctance, which is R3 plus RG times phi 1. So that's the two equations you are going to use. If one is given, or reluctance is given, R1 and R2, and R1, R2, R3, RG. So you make a matrix, or even using a calculator, solving two equations and two unknown. So the known values are F1 and F2, and the reluctance or reluctance, and all reluctance known. What's unknown? Phi 1 and phi 2. Two equations to unknown. So easy to solve using any technique, linear and then find phi 1 and phi 2. I did that, and I found that phi 1 and phi 2, they are equal and expected because it's symmetric. R1 is equal R2, F1 is equal F2, and 1 in the middle. So phi 1 and phi 2, I found that they are equal to 0.07 times 10 power minus 4 Weber. So that's, I mean, the answer when you do solve the two equations, phi 1 and phi 2. Yes. Oh, yeah. So you get phi 1 and phi 2, the values, and they are equal. The question is find the air gap flux. Well, the air gap flux, it's the total, phi 1 plus phi 2, as you said. So you say phi g, that's the first part of the question. Phi g is equal phi 1 plus phi 2. So it will be like the double of the quantity that you got there. That would equal 4.134 10 to the negative 4 Weber. So as you see, we solve the magnetic circuit like any electric circuit. So when first you came to the class, you said, okay, that's a very complicated one, right? You look at it. It's complicated. No, but if when you make it as a circuit, it's not. But just you have to be careful about the dimension, make your circuit, and apply anything like mesh voltage method or node analysis, whatever you can. It depends on the problem itself. Well, so that's the first part. Find the flux in the air gap. The second thing that was find the air gap flux density. We want the density. Flux density or magnetic field density in the air gap, it's B. So now we got to know what is the relationship between flux and flux density. We explained previously, and I'm going to remind you, if you have this is the core, and that's the cross-section area, and the flux going in this direction perpendicular in the area. So the flux density is equal flux phi divided by the area of the cross-section area. That's the density. Means for every inch square, what do you have? So Bg is equal to phi g divided by air gap. And we're assuming that the dimension of the whole core, they are the same, symmetric. Can they be different? Yes, but will be given the problem, like the cross-section area is different than there, would be unsymmetric. So I have 4.134 times 10 negative 4 divided by the area, which is equal to 410 negative 4 meters squared, 2 by 2 centimeters, I said before. In this case, we can find the flux density. It's equal 1.03, and the units is Tesla or Weber per meter square. Both are the same. Tesla means Weber per meter square. So we found that the air gap flux density. The last question in this example that to find the magnetic field intensity. Magnetic field intensity, which is H. So how can you find H? We know that there is a relationship between the magnetic flux density and magnetic field intensity. We did it before using the curve. If you remember, we did that something like that. We said this is H and this is B, and in the core will be like that. So B is equal mu times H. You know that. So if you're talking about the magnetic field intensity in the air gap, so you can say Bg is equal mu naught H. If you are talking about the core, inside the core, it's mu C H. C and mu C, it's equal mu naught mu R. The question was about the air gap. So I'm going to use this. So Hg, which is the magnetic field intensity, Hg will be equal to Bg divided by mu naught. And Bg, we got it. You just got it in part B. And it was how many Tesla? It was like 1.034 Tesla. And mu naught, as you know, it's 4 pi times 10 power negative 7. We get equal 0.822 times 10 power 6 ampere turn per meter. So that will be the magnetic field intensity. So in the end, it's not bad. Even it looks bad in the beginning, just like complicated, but it's not. When you use electric circuit analogy to solve it, it's just not. Actually, it's a very simple circuit. There is no dependent source or anything. Pardon?
What are those units? 18
per meter. And why it's, let me just make it here, and I'll tell you why it's, the unit look like that. Because if you remember Ampere's law what said HL, the integration of closed path, HL is equal NI, right? And when it's simple case, so H, when you have straight line, so H times L is equal NI. So what's H? Is equal NI divided by L. NI, ampere terms, I is ampere, N is turns. You can write it T capital, T small, whatever, but I mean, like to make it small to distinguish between Tesla and terms, divided by L, which is meter. That's the unit of H. Any question on this example? It's very important. This is the last example I'm going to solve in the magnetic circuit. I just have found that when I make this, then I have the right to give you any problem to think about it using circuits. Okay. Yes.
This is example also in the book.
Yes, it is. It is from the book. Yeah.
What page would it be in the book?
No, I will never remember the page. I'm very happy and lucky that I remember the name. But in any way, it's the same example, and I just put even, and that's why when I put the example, I just put it as it is from the book. Same graph, I got it, I put it so. And some student asked me this morning just to post the handout in PDF. Even I have the videos, so I did post it today. So when you go now again to the folio, you'll find not only the videos and also the handout, whatever I wrote. And I started to do that, so I mean you can have when you read something, when you are watching, when you read also you can have both options. And the same thing I'm going to do that. It's going to not be only just video. I will put also the PDF. Okay. Inductance. How can you calculate the inductance? L. You know that. You dealt with L in circuits. That's equal 2 Henry, 3 Henry, 10 Henry, whatever, the inductance. So to calculate the inductance of this system, we got a core here. The cross section A is equal A. The current is equal I. The number of turns is equal N. And the path has a length of L. And we need to find L. The main equation or relationship of L, we say that the flux linkage is equal L times I. That's the main equation that we need to understand. What's flux linkage? Is the total flux intersecting the whole coil. Like when you have coil of N turns, and each turn there is flux linking. I added them. If you have, let's for example say, if the flux is equal 10 Weber, and then you got one turn. So the total flux linking, it's 10 times 1, 10. If you got 2 turns, you got now 20. If you got 30, and so on. So in phi, it's the flux linkage that's responsible for the whole magnetic field system. So they said that there is a relationship between the flux linkage and the current. The quantity of the total flux linking all this term depends on the current. There is a relationship when the current increases, the flux linkage increase. The constant that relating that's L. That's L. That's the inductance. That's the main definition of the inductance. How do you get it? So L is equal to the flux linkage by I, and we know that the flux linkage, let's take it step by step. It's equal the flux times the number of turns. You get the total. Well, now what is the flux? How can I can get the flux if I know the flux density? The flux is equal flux density times the area. The area of the core given here. Remember, I'm trying to find the inductance of the system. Just I sketch it here. This core with the coil. I want to find what's the equivalent inductance. So let's continue. So NA times B. What's B? I'm trying to get closer to something related to the current. B, it's related to the H. Right? B is equal mu H. B is equal mu H. I just explained the previous page. So you have N, A, and B is equal mu H, mu H. I'm getting closer to the current. Is there a relation between H, the magnetic field intensity, and the current? Yes. Ampere's law. Ampere's law said that HL equal NI. So I'll say it's equal N, A, mu, and H will be equal NI divided by L. Well, I'm not going to do that. I will leave it H. I will leave it H here, and I use the relation with current here on the bottom. I have the current here, so I just find the relation between current and H is better. So from here, I can write the current I is equal HL. You can get it from both ways, but I prefer to get rid of the current here. So that's lambda, which is flux linkage, and to find L, I divide it by current, right? Divided by current. Now I can replace I by this equation HL by N. So it will go N on the bottom, go on the top will be N squared. H cancel H. I got mu in the top. I got A in the top. I got L in the top. Remember, do you remember the reluctance? What's reluctance? L over mu A. So what is 1 over reluctance? Mu A over L. So just that's what I have, mu A over L. So it's equal N squared divided by reluctance. So L is equal N squared divided by the reluctance. I got expression for the inductance of a system has core and coil on it. This is the inductance, equivalent inductance. I find the number of terms, I square it, I calculate the reluctance of the path where the flux go, divided, I got L. That's how we get L. Not to be given to you 2 Henry, 3 Henry. No, I can calculate it now using the dimension of the core and the permeability of everything from material, dimension of the material and property of material, which is permeability, and the source N squared. So that's the way how you get the current expression. So in this example, if you have N, yes.
Do we need to derive that equation?
Do what?
Derive that equation.
No, you got to understand how to drive. But don't drive it. But when you have a problem, you don't have to drive it, or it is given. Except if I ask you, for example, I give you some system different than that. I ask you to find the inductor. I give you some circle, and I ask you, then you start to follow the same steps. But if you have system like that, like in this example, then you use the results. All right. So N is equal 400. LC, the length of the core is equal 50 centimeter. Air gap length is equal 1 millimeter. The area of the core equal the area of the air gap is equal 15 centimeter, the relative permeability of this material is equal to 3000, and the current is equal to 1 amp. And the question is, find L. And as you know, to find L, you got to find first the reluctance. I gave you already this system will have two reluctances, one for RC, one for RG, and then when you add them, you get the total reluctance. Then you can find the phi. You can find phi, or just you can find the reluctance or L by n square over the total reluctance. So go ahead, get the paper, put your name on it, and get me the inductor. You already know the formula. I give it to you. That's L is equal n square over total reluctance, and get the inductance of this system. You don't have to derive the equations. We already found n equal n squared divided by reluctance, right? And I give you the hint. The difference between this example and one I just proved that there is air gap. The air gap, it means the reluctance will change. You have R plus R, RC plus RG. So go ahead but please make your name clear, because sometimes I have problem when I try to figure out the name.